Hi everyone, my name is Justin Hall, and today I'll be presenting the paper DeepTest, Automated Testing of Deep Neural Network-driven Autonomous Cars. Now, it's a bit of a mouthful, um, but I really found the paper interesting because it proposed a new category of black box testing for AI that I thought was extremely interesting. So now the basic paper premise is, like the title suggests, they are developing a testing framework for self-driving cars, and particularly the deep neural networks, or DNNs, that power self-driving cars. So their first thing is that activating more neurons of a deep neural network reveals edge case behaviors. I've heard of a lot of cases where a convolutional neural network will try to inference an image, right? Basically, it tries to look at an image and detect objects in it. And if you add staticky noise or some kind of input that it's not expecting, it'll act crazy. It'll say, oh, that stop sign isn't a stop sign, that's actually a banana, right? Was one famous case. Or if people put stickers over their faces, like one side of their faces or something, it won't realize that you're a person anymore. Okay? So they're positing that activating more neurons, right, reveals edge case behaviors like acting crazy. And for DNNs powering self-driving cars, altering normal driving images, right, changing them up a little bit, increases that neuron coverage. So that's another key fact. And the last one is that the DNN performance improves when you train on these altered images, which I think is called network hardening, right? That's a colloquial term that most people use. But these are really interesting things. Okay. Now, why should you care? Obviously, this image has an impact on you. The effectiveness of self-driving cars is inherently tied to passenger safety, right? If these DNNs and networks and everything are not safe, like you haven't tested all of the possible edge cases and all of the possibilities, which we know from test in class is extremely expensive and costly, then people are going to get hurt. And people already have been hurt, right? The person in this car crash died because they couldn't tell the difference between the white semi truck against the mid morning light background of the sky, right? So that was an edge case that wasn't discovered until someone had to pay the price, right? And as a second thing, developing innovative AI black box testing methods is extremely cool, and we're going to need that in the future. So that's why you should care. All right. Now, as always, I'm going to include a basic neural network DNN explanation here. Um, so, deep neural networks are vast structures of interconnected layers of neurons. As you can see the picture here, here's a neuron, right? It's like one node where you have an input. There's some kind of function in the neuron, and then you get an output, right? And DNNs are these vast, like layers upon layers upon layers, thousands, tens of thousands, sometimes even millions of neurons connected for the purpose of converting an input into an output. I always think about it like imagine you have a robot arm and it can have an infinite number of neurons or an infinite number of joints, right? The neurons are joints. And so trying to get a basketball through a hoop, as you add more joints and more neurons, there are many, many more ways that you can get the basketball through the hoop. But because these structures are so huge and so complex, they're often seen as a black box. We can kind of tell what happens at each stages. Like at one stage, it determines shapes, and at another stage, it figures out that those shapes are a stop sign. Remember, for example, or a road, and we can kind of tell what it's doing at each stage. But again, it's so huge, so complex, and there's so many possible ways for it to act that it's effectively a black box for us. We can tell the structure, but it's a black box. Okay. And now, again, whoop, for self driving cars, you take the camera input, LiDAR, IR sensor, and it goes through the network, and then it determines your steering angle, your brake, and your acceleration, right? That's basically what cars do. Okay. So for their paper, they took several winners from a 2018 Udacity challenge. The first one was, and actually, let me talk about this first. Convolutional neural networks take an image, and then they use convolution, running filters through it to determine edges and everything, and eventually it comes up with an output. In this case, steering angle. Uh, RNNs, which are recurrent neural networks, are less about images and more about memory. So as you see here, you get an input to a hidden layer, and then that input gets fed into the hidden layer. The decision and the steering angle and everything gets fed back into it. So it kind of looks like this if you unroll it, where you get multiple outputs, and it kind of remembers. So that's a part of each one of these. I put some images here because it helped me remember which one was. Right now, the first one was chauffeur. It was one CNN to determine the pictures, and it was one RNN to remember, what actions it was doing previously before and the effects that they had. Now, chauffeur, I think about, a driver with a map, right? The map is kind of like the RNN, and the CNN is like the driver. He's looking at it and he's trying to say, okay, this is what's going on. The map is constantly changing. It's the RNN. Sorry. Rambo, which again I really wanted to put a picture of the movie, but it's three CNNs, and the actual action it takes isn't any one of the CNNs. It's actually a combination of the differences between their outputs. That's what it actually goes with. And for that, I think about the three-headed knight from Monty Python, where they finally come to an agreement, but they're still, it's only through arguing with each other that they come out with a plan of action. So think about Rambo as that, and Epoch is just a normal CNN. So it really is just this. Okay, so the first thing they thought was, okay, we are going to modify these images. As you can see right here, this is from the paper. They're going to modify the image with a variety of different transformations and effects and, my bad, and they're going to see what that does. Now, they're generating synthetic data here, which is always an exciting thing because synthetic data allows you to get more data than the manually collected and transcribed, or sorry, manually, uh, thinking of the word here, annotated. That's it, manually collected and annotated data. So brightness and contrast are basically filters that you can add. Translation, scaling, rotation, and horizontal shear are affine transformations that, as you can see, translation and rotation, we get scaling is zooming in or zooming out, right? And horizontal shear is a little bit of, in my opinion, where it just takes off a little bit of the image right there. Algorithmic blurring, like Gaussian and other algorithms, is applied. Fog effects, like this, are layered over top, and also rain effects. So it's really interesting to see, like, oh, if it's the same situation but it's raining, what happens, right? But not too much. A main, like, the validity of the author's assumptions here is based on the fact that their transformations are metamorphic, which basically means that most of their changes don't change the driving scenario, right? They're not adding pictures of cars in different locations, and they're not changing the shape of the road or the terrain right here. It's just adding forms of noise, right? And with the exception of rotation, if the camera is rotated by 30 degrees, yeah, there better be a different action, right? Now, based on this, any significant change in the driving direction or angle is considered an erroneous behavior. Because again, there is no difference here, right? Other than maybe the image is slightly wrong, which could be caused by the camera shaking or a malfunction, right? But the actual driving scenario is the same. So any major change is, as you can see here, incorrect. If it followed this, it'd drive you right off the cliff right here. And any errors were reviewed by the authors to determine whether they were dangerous, as in these cases right here. There are also some false positives, right? So it was enough to trip, like the difference was enough to trip the system, but this would not cause you to crash here. So there you go. CYN, cover your neurons. Again, the whole idea is that, and this is kind of like a black box testing technique, right? Where you assume that tests that cover more lines of code or more logic branches are better, right? And so they said, what happens if we try and maximize neuron coverage here with our image alterations? And they did some tests using the Spearman correlation and the Wilcoxon. I assume that's how it's pronounced. My apologies there. And they found a strong correlation between increased neuron coverage and changes in steering angle and direction. So they said, okay, there is a correlation here, and the more we fire up these neurons, the more neurons we impact here, as you can see, like the difference here, they figured out that those are better tests, and they reveal more information about how the network will react in any situation. And using guided image alteration, which is where they, again, kind of place the hands on the scales there, and they added uh, image alterations from the previous class right here. They did it in a smart and intelligent manner. They figured out that they could almost double neuron activation coverage from before and after using that. So doubling neuron activation coverage is really good when you're trying to figure out edge cases, right? It's kind of like if you have to drive to work, excuse me, if you have to drive to work in the morning and you just take the same route, your brain is going to be shut off. You're not going to be thinking, right? But and that's how accidents happen, right? Because if a car suddenly jumps out of nowhere, you might get into a crash, right? But if you're actively alert and aware and thinking on a different route to work every day, right? You're going to be much more aware and you're going to be safer. So that's kind of the thought process there. Now, how'd they do, right? It's a lot of good talk, but how did they actually do? They proved the neuron coverage relationship. As I said, they approximately doubled, right? This is baseline versus guided generation. They approximately doubled, or even more than doubled, in the case of Rambo S2 right here. Remember those three networks of Rambo with the three-headed knight? So they more than doubled neuron coverage, right? And they proved that relationship, which is incredibly important because now you have a new tool in your toolbox when you're testing these big neural network black boxes. Okay, so really important. Second of all, they detected 1,000 plus instances of erroneous behavior. Now they have different lambdas of significance right here. More higher levels of scrutiny, the higher the lambda is. They went for 5 for an average, and also this is the difference in mean squared error for their outputs. So again, the more stringent is right here. Where is the difference? But they picked these. They picked this to showcase, right? And you have to pick something to showcase, and like having all these numbers, I can tell you, is a little bit confusing. But they determined that using one transformation, you get these numbers. 330 is what they picked, and particularly like erroneous behaviors, right? For fog, rain, and guided search. Fog just wow, it's crazy how much that impacts it. And again, it's different between the networks. They noticed that, for example, shear Rambo had a lot of problems with shear problems, but Chauffeur and Epoch did not, right? And vice versa for translation. Rambo's like, no, I see it. Chauffeur and Epoch were highly confused, and they were all highly impacted by fog. Rambo most of all, right here. Okay, so again, they discovered those 1,000 plus instances of erroneous behavior. Right? Apologies for that. And here's an image right here where you can see again, dangerous, right? And so they said, okay, we figured out tests and images that cause these bad behaviors, but what can we do about it? Can we fix it? So they retrained the networks on synthetic data to perform up to 40%, and my apologies. And then they can perform up to 46% better. Here, this is the mean squared error of the outputs versus the annotated correct course of action right here, and it might seem to be a slight improvement, but with mean squared error, each reduction is highly impactful for making the right decision whenever you're driving. Right, it's a game of inches. You don't have to hit you can miss the car by an inch and you succeed, but if you hit the car or you go off the road, that's a problem. So perform up to 46% better, which is a good thing. All right. Now, I really want to thank you for listening to this. Please do check out the paper if you can right here in DeepTest. Here's the note. And they also provided a GitHub for with more results of erroneous behaviors and their altered images. You can scan this link, and the links to the paper and their website will be in the video below. Thank you so much. I hope you have a good day.